Hello student, welcome to lecture 5. Today we are going to discuss factors influencing solubility of drugs. So, what are the factors which influence the solubility of a drug? The different factors which influences are, first is the solute. Under solute we have to understand the particle size, shape and surface area. Then the physico chemical properties like the melting point of solute, then molar volume, etc. are the physico-chemical properties which influence the solubility of solute, and the physical form. Under physical form, the salt form, the crystallinity, the salt form, crystallinity, polymorphic form, etc. Decides how these affects the solute solubility in solvent. Then this is the first factor, that is solute. Then after solute it is the solvent. It depends on the nature of the solvent. Nature of the solvent, pH of the medium and volume of the solvent. In nature of the solvent, basically it deals with the polarity of the solvent. We will discuss this in details. Then after solvent, then comes after solvent there are environmental factors. Which influences the solubility of drug. What are the environmental factors which influences the solubility of drug? That is temperature, and pressure. Then apart from these three, that is the solute, solvent and environmental temperature, there are also other factors like common ion effect, missile formation, that is addition of surfactant, and then addition of other ingredients. Because when we formulate a dosage form, apart from drug there are other ingredients which are also present in the formulation. So, they also affect the solubility of the solute in the solvent, that is the solubility of drug. Then we will study some of these factors in details. So, first we will check the effect of temperature on solubility of drugs in solvent. See, if the temperature drops, that is if the reaction is a endothermic reaction, if the temperature drops while we mix the solute and the solvent, then with increase in temperature the solubility will increase. That is, if the reaction is a endothermic reaction. Okay. When the solute is added to the solvent, if the temperature drops, that is, if there is a positive change in the temperature, that is, if it is an endothermic change, then with increase in temperature of the system, your solubility will increase. And most of the pharmaceutical drugs falls into this category, means they shows endothermic reactions. And best example is potassium nitrate when it is added to water. Then with increase in temperature, the solubility of potassium nitrate is increased in water. Then comes if the temperature stays neutral, means there is no significant gain in heat, or there is no loss of heat, or we can say no heat is absorbed nor heat is liberated. That is, if the temperature stays neutral, then with the increase or decrease in the temperature there will be insignificant effect, as for example, sodium chloride solubility in water, it is least affected by the change in temperature. Then the third one, if there is a increase in temperature when the solute is added to the solvent, then what happens? With rise in temperature the solubility decreases. With rise in temperature the solubility decreases. Example is calcium acetate, when it is added to water, its solubility decreases if the temperature is increased. And here these are basically exothermic reactions, means heat is liberated. As heat is liberated in this case, with increase in temperature the solubility decreases. Then comes your pressure. See, this pressure factor is very important when we are considering the solubility of gases in liquids. So, if the pressure is increased over the solvent, then the solubility of gases increase, and this has been confirmed by your Henry's law. We will study in details about the Henry's law when we will study the solubility of gases in liquids, and we should have a preliminary idea that was what Henry's law states. It states that if the solubility of gas, that is solubility of dissolved gas, is directly proportional to the partial pressure of the gas above the liquid. Partial pressure of the gas above the liquid. Suppose this is a container and here we have the solvent. You can see here we have the solvent, and here above we have the gas molecules, and here we have a piston, okay. And sidewise what I did, we just applied force or pressure on the piston. Okay, just a minute. Okay. Okay. Piston. As this piston is moved, as the piston is moved downwards, so pressure is exerted on the gas molecules which are present above the solvent. Here the solvent is there, and some of the gas molecules are now dissolved. So, it is, so I am writing here the solution. So, when I am applying pressure, the gas molecule will strike, it will strike the surface of the solvent or the solution, then more of the gas molecule will enter into the solution, So, this is about pressure. Then comes salting out. If we add salting out means liberation of gas. That is, if we add electrolytes like sodium chloride, or if we add non-electrolytes like sucrose, these are basically polar, you can say polar non-electrolytes. Okay. So, if we add these additives, that is electrolytes and non-electrolytes, to a solution of gas and water, then what happens? These electrolytes have affinity. These electrolytes have affinity toward water. So, the water molecules are attracted towards the non-electrolytes or towards the electrolytes. So, as the water molecule is attracted towards these, so the water molecule which has dissolved this gas molecule, the amount of water molecule decreases, which holds this gas molecule, or we can say the attraction force between the gas molecules and the water molecules decreases. Why it decreases? Because the attraction force between the electrolytes and the non-electrolytes increases with water. So, the gases are liberated. So, this is known as salting out. Then comes the chemical reaction. There are certain gases like hydrogen chloride, ammonia and carbon dioxide. They do not follow Henry's law. Why? Because when these gases are passed through the solvent, they react with the solvent, and due to the reaction with the solvent, their solubility increases. As they react with the solvent, so their solubility increases, and we cannot apply Henry's law in this case. Why? Because the limitation of Henry's law is, if the gas and the solvent reacts with each other, then Henry's law is not applicable for such type of gases. Now, so as the chemical reaction takes place between the gases and the solvent, so there is results in an increase in solubility. Then comes influence of foreign substances. Now, when we talk about the influence of foreign substances, now when we talk about the solubility of, suppose this is a solute, suppose A is a solute and B is a solvent. Suppose B is a solvent. Okay. So, when we talk about the influence of foreign substance, now if in a solution we have a combination of solute and solvent, so it comprises of a binary system. Why binary system? Because we have two components, that is the solute and the solvent. So, two components are present, so it is called as binary system. And when we are adding a foreign substance to it, that means what we are doing? We are adding a third component. So, as a third component is added, so now it will produce a ternary system. You understood why we are calling it a ternary system? Because previously we had the solute and the solvent. So, it was a two component system. Now, we have added a third one. So, it is called as a ternary system. Now, if mainly this influence of foreign substance is mainly seen when we are talking about the two liquid pairs. So, even if you use two liquid pairs, the one of the liquid will act as a solute and one of the liquid will be solvent. Okay. So, suppose we are adding a third component, that is C, okay, and if the C is soluble only in one of the liquid pairs, means if it may be soluble in the solvent or it may be soluble with the solute. So, suppose here C is soluble with this solvent B. Then what happens? The mutual solubility of A and B, there we can write it here, I can show you here, the mutual solubility on addition of this C, which is soluble in this B solvent, their mutual solubility of this liquid pair, mutual solubility of this liquid pair, decreases. It decreases if your third component is soluble only in one of the two components, then the mutual solubility of the liquid pair decreases. Then comes the second case. If again we have taken one solute and one solvent, one liquid act as a solute and one is your solvent, and we are adding a third component. If this third component is soluble in A as well as it is soluble in B, here we can see it is soluble both with A and B. If it is soluble both in A and B, then the mutual solubility of whom? Mutual solubility of A and B. Mutual solubility of A and B increases. Mutual solubility of A and B increases. Here we can see, as it is written here, if we add a substance is added which is soluble in both the components, then the mutual solubility of the component pair increases. Then we will study the effect of pH. See, most of the drugs which are present in which are found in pharmaceutics, they are either weak acid or weak base. So, their solubility depends on the degree of ionization, or we can say it depends on extent of ionization. Now what happens? It depends on degree of ionization, which is related to pKa and pH, pKa, it is the dissociation constant, and pH is the pH of the medium. So, the ionization, extent of ionization depends on ionization depends on your pKa and the pH of the medium. Now, we all know that when we talk about the solubility, solubility depends on number of ions. If the number of ions is more, then the solubility will be more. If the number of ion is less, then the solubility will be less. That means, the pH at which the drug is entirely in the ionic form, then it starts behaving like an strong electrolyte, and then it gets solubilized in the given solvent. So, as it gets solubilized in the given solvent, the solubility increases. So, we can say that it offers no solubility problem if it is present if it behaves like a strong electrolyte, that then we can say that if its number of ions are more, that if it is present in ionic state. Okay. Then comes, and its ionic state is related with pH and pK. Then the next is the common ion effect. Common ion effect, and this is applicable for sparingly soluble electrolytes. Suppose we have a sparingly soluble electrolyte, that is AB, and as it dissociates, as it suppose we have AB as a sparingly soluble electrolytes, and as it dissociates, it gives A plus ions and B minus ions. Now, if I add a if I add a second electrolyte, that is Cb, if I add a second electrolyte, that is Cb, and it possesses the similar ion as that of the sparingly soluble electrolyte. Suppose, as we can see here, this B is common, this Cb also contains B and this Ab also contains B. So, this B is in common. So, as this B is in common, if I add this, if I add this Cb to this Ab, as this B is present in abundance, so the forward reaction is retarded. So, there is no forward reaction. So, if there is no forward reaction, that means the formation of B minus ions will also reduce. That means, if the forward reaction is retarded, that means we will have most of the AB as undissociated. So, as it is undissociated means no ions will be formed, and we know that solubility depends on number of ions. Number of ions is more, then solubility will be more. But here, as we can see that the number of ion is less, so the solubility is less. So, as we add this second electrolyte, as this B is in common, so the dissociation of AB, that is sparingly soluble electrolyte, is decreased. So, as the dissociation is decreased, then what will happen? As this dissociation decreases, the number of ions formation will be reduced. So, as the number of ion formation reduces, that means the solubility will decrease. Then suppose another case may also occur. What? Suppose if we are adding this, suppose we are checking the dissociation of the sparingly soluble electrolyte, and I have added a second electrolyte, but now you can see the difference. There are no common ions in both the electrolytes. CD is a different electrolyte and AB is a different electrolyte. And if this CD has the property to bind, if this CD has the property to bind with the electrolytes which are bind with the ions which is produced by the dissociation of these electrolytes, then what happens with the addition of these electrolyte which does not have a common ion, rather what it does, it combines with the ions which are formed. That means, it is decreasing the concentration of B minus ions, and what is happening as the concentration of B minus is reducing, the dissociation of AB proceeds in the forward direction. As the dissociation proceeds in the forward reaction, that means what? More of this AB starts to dissociate. So, more dissociation means more ions means more solubility. So, in this case the solubility will increase. Okay? This is just opposite to your common ion effect. Then comes After this, we will study about the influence of solvent. Now, for the solvent, we have studied lot of this solvent that like dissolves like. In our last lectures also, we studied that the main empirical principle which guides the solubility is like dissolves like. Okay. So, more like this means if the solvent is polar in nature, then it will able to solubilize polar solute. If the solvent is non-polar in nature, then it will able to solubilize non-polar or dissolve non-polar solute, and the same goes for the nature of the solute also. It depends if there is a structural similarity, as we can see here also we can study this where it went, yes, here also we can see this nature of the solute and solvent. So, if there is a similarity between structure and property between this solute and solvent, then they will dissolve in each other. Polar solvent dissolves polar solutes and non-polar solvent dissolves non-polar solutes. So, then again, yes, then comes the influence of co-solvent. So, combination of the solvent shows better solubility. Now, what happens when we talk about these co-solvents? Basically, we have seen that co-solvents increases the polarity of the solvents and it increases the solubility. Suppose there are certain drugs like phenobarbital and its solubility in water is 1.3 grams per liter, 1.3 grams per liter. Now, if we add a co-solvent of ethanol, then its solubility is increased to 3.2 grams per liter. Now, what happens? We actually what we do to find out this, we find out the solubility parameter. Now, when we add this co-solvent, we first find out the solubility parameter of the solute, and if we want our solute to be soluble in our solvent, then the solubility parameter of the solute should be equal to the solubility parameter of the solvent. Now, in case the solvent solubility parameter and the solute solubility parameter differs, then what we do? We add other solvent like co-solvents, so that the solubility parameter of the solvent blend becomes equal to that of the solubility parameter of the solute, and in this way the co-solvent makes the solute makes the solvent more appropriate for the investigated solute. And like this we will the next class we will discuss on the other factors which are left. So, for then, thank you.